Well, this example is going to give us there we go. It's going to give us a 10 kilogram ball going around with a constant radius of 2, right? And it'll break if we get over 100 newtons of force, which is pretty typical to have a material with a certain force constraint, right? It can only take a certain amount of stress before it breaks. So we could come up with a force that's allowed in that cord. And we need to find out if it will break, right? If it's going, let's see. Let's see what this is saying actually. It's got a velocity of 3 meters per second when it's at A, and it's in a vertical path. So, meaning this is spinning, right? It's going down and then it's coming up and then down and then up. Right? It's not on a table or something. It's actually mounted on a wall or whatever it is, spinning around that peg on a vertical path. Meaning we're going to have to include its own weight in that motion, right? So that'll be important. We won't include gravity as an acceleration. We'll include it as a force. That's typically how we'll do these. So we need to find whether the cord will break and the increase in the speed of the ball at that instant. All right, so let's try it out. It's definitely got a constant radius, so the nt will work nicely. We know its velocity, so we've already got v squared over rho handed to us. And let's see, any other information, we'll plug it in as we go. So let's draw in our free body diagram. The tangent path here, as it's going around that circle at that instant, would be downward like that. And the T is this tension in the cord. That's a force going inward on the curve, so that would be 100% in the normal direction. So you're probably starting to see where this is going. We need the normal acceleration to figure out what that T force is, right? But what we need to not forget is that that's not the only force now because it's a vertical path. So now the weight also will weigh in, so to speak. So that'll be pushing down like that with whatever its mass was, 10 kilograms times 9.81. So that'll be our free body diagram. So we've got all the forces on there. Now we need the kinetic diagram, draw our axes again, and we've got MAN and MAT. So those are equal to each other. Now we just need to come up with some equations. So the sum of the forces in the N equals MAN. So let's sum the forces in the N. We've got, looking back at our picture, T going in the positive direction, and we've got W cosine 45 going in the negative N direction, right? So that's pointing down this way. So that's where that's coming from, or sine 45, depending on how you did it, how you drew it, equal to the mass times acceleration in the N direction. So if we wanted to solve for that AN, we know that that normal acceleration is equal to v squared over rho. So we plug in 3 meters per second for v, the 2 meters for rho, and that's just plugged in like that. We've got the mass of 10 kilograms plugged in, and we've got the weight is 10 kilograms times 9.81, so that is plugged in for W there. So we've got everything plugged in and we solve it for T. We end up with 114 newtons. So yep, if it's going that fast, that's too much for our little cord, which could only take 100 newtons. Right? So the cord would break. Kind of interesting application there. We also need to define the increase in the speed of the ball. What does that mean? The increase in the speed, ooh, that sounds like a change in speed, a rate of change of speed, which would be the acceleration in the t direction. So that's what we're doing here. We could solve this for at. We'll need to sum the forces in the t direction, which in the t we only have w cosine 45, right? That would be in the positive t direction, equals mat on the kinetic side. So that's what we've got here. W cosine 45 equal mat. We know the weight, so we can plug that in. We know the mass, so we can plug that in. So there it is, the weight, the mass of 10 kilograms. Solve that for AT. And even though we didn't know a velocity relationship with t, right? We didn't have a function that we could do dv dt. We could still solve that for AT, and we get that instantaneous tangential acceleration as well. All right, so that is it for that problem. Pretty classic example of what we could do using the NT system when we say force equals mass times acceleration.